Hello everyone. Today I'm going to demonstrate about QAM Virtual Laboratory. Before explaining the interface, let me briefly explain what QAM is. QAM stands for Quadrature Amplitude Modulation. So QAM is a method used to send digital data like internet data, mobile signals, Wi-Fi signals by modifying the carrier waves. Instead of sending just 0 and 1 directly, QAM changes the amplitude and the phase of the carrier signal. Here we have two carrier signal called in phase and quadrature phase. Now let's move to the website. Right when you open the website, you will notice a clean interface with a futuristic lab design. The platform is divided into multiple sections like aim, theory, procedure, pre-test, simulation, post-test, and result. In the aim section, you get a clear idea of what you're going to learn. This includes understanding how QAM works and how signals are generated and how different modulation levels affect performance. This also includes objectives and tools and APA section. Here, the concepts are explained in a simple way without overwhelming you. You will see the equation, signal representation, even the block diagram showing how QAM works step by step. QAM system has two main parts. One is transmitter and another one is receiver. First, let's see about the transmitter part block by block. Data source. This generates binary bits like zeros and ones and then serial to parallel converter. As we know that QAM send multiple bits per symbol. So in serial to parallel converter, we group bits. For example, 16 QAM. Let's take 16 QAM. 4 bits per symbol, like 4 bits are grouped per symbol, and then QAM mapper. It is the most important block. It maps each bit group into the constellation point. Gray coding is used so that adjacent symbol differ by only one bit. It reduces the error probability. Now the signal is divided into two branches, I branches and Q branch. In I branch, it's multiplied with the cos 2 pi fc of t, and in Q branch, it multiplied with the sin 2 pi fc of t. This creates the final QAM signal. And in combiner, both I and Q signals are added together. And finally, AWN channel. Uh, AWGN means additive white Gaussian noise. This adds noise to stimulate real world condition. Next, in the receiver section, the noisy signal enters the receiver and it's again multiplied with the cos 2 pi fc of t and sin 2 pi fc of t to separate the I and Q components. And the low pass filter removes the unwanted high frequency component to get clean I and Q values. Then the decision device. It decides which constellation point is closer. So it decides the most likely transmitted symbol. And then the demapper. The demapper converts symbol into original bit. And finally, the data out. Like we'll get the original reconstructed data. This is the example for constellation diagram and the applications of QAM and key concepts that are included in the QAM, like symbol rate, gray coding, and eye diagram, etc. Next to the pre-test tab. Here you will have the set of questions that checks our theoretical understanding before performing the experiment. And the next tab is simulation. This is the most important tab. This simulation allows us to analyze 4 QAM, 16 QAM, 64 QAM, and 256 QAM by adjusting the parameters like SNR, amplitude, carrier frequency, symbol rate, and number of symbols. We can observe the effects of waveforms, IQ baseband components, constellation diagram, and eye diagram in real time. First, I'm going to select the type of QAM I'm going to work. I will select 4 QAM and then SNR controls the noise level. Increasing SNR reduce noise and improves quality. Decreasing SNR increases distortions. And then amplitude controls signal strength. And carrier frequency determines how fast the carrier oscillates. Symbol rate defines how many symbols are transmitted per second. Number of symbols controls the simulation length. After seeing the parameters, we click Run Simulation. And this is about the reference input. And the next step is about checking the waveform. At the top, CH1 shows the reference carrier input and the channel 2 shows the QAM modulated output. We can observe the amplitude and phase changes depending on the symbol mapping. If SNR is reduced, noise distortion becomes variable in the waveform. We can also zoom in and zoom out the waveform. And then IQ baseband componentism. We can observe two signals here. One is in-phase component and another one is quadrature componentism. These are the digital amplitude levels that represent symbol mapping. The I component multiplies with cosine carrier and the Q component multiplies with the sine carrier. Together they form the QAM final output signal. Each change in I and Q levels corresponds to the different constellation point. This clearly shows how both amplitude and phase are varied in QAM. Next to the constellation diagram, it displays the in-phase and quadrature component plots on x and y component. This is the constellation diagram for 4 QAM and for 16 QAM. It has 16 points, and 64 it has 64 points, and 256 it has 256 points. With the high SNR, points are sharp and clearly separated, and with low SNR, points spread away from the ideal points, indicating noise impact. And this is the eye diagram. Eye diagram shows multiple symbol intervals overlapped together. To check it, look at the center eye opening. If the eye is wide open, signal quality is good. If the eye starts closing, noise or intersymbol interference is present. If the eye is almost closed, distortion is high and bit error probability increases. When SNR decreases, eye becomes narrow or noisy. A wider eye indicates better system performance. Post-test tab, it evaluates what we have learned after performing the simulation. Unlike the pre-test tab, these questions are observation based. And finally, in the result section, you can see your pre-test score, post-test score, and the improvement score. And these are the key learning outcomes and the modulation comparison table for all 4 QAMs. And it tells about what you have understood from the whole website. And this is all about the website. Thank you.